My name is Tombolaza Filamant. I'm a PhD candidate at University of Thomas in Madagascar. Today, I want to share a result from a 5-year randomized controlled trial on digital agriculture in Madagascar, a country that is both one of the most climate vulnerable in sub-Saharan Africa and one with almost no experimental evidence on what works for smallholder adaptation. I will show you that combining climate forecast with digital economic extension produce like robust productivity gains, and I will explain why we believe these effects are causal and what they imply for policy. Let me start with the context. Madagascar is not a typical case for digital agriculture research. It is an extreme case. Three fact standard. First, rice is the backbone on the rural economy, yet smallholder yield of 1.7 to 2.1 ton per hectare are less than one-third of the agronomic potential of 6 to 8 ton per hectare. The yield gap is enormous. Second, climate risk is severe and perennial. Madagascar receives 3 to 4 named cyclones every year, primarily between November and April, which is exactly the main rice growing season. In drought year linked to El Nino, cross loss can exceed 20% of planted area. Fact, the information infrastructure is almost completely absent. Only 28% of our Brazilian households had received any agriculture extension visit in the previous 1.2 previous 12 months. The national ratio of extension officer to farmer is 1 to 1,500, nearly 4 times worse than the recommended ratio of 1 to 400. Yet mobile phone ownership is 68% and rising. This creates an opening for digital advisory service to fill the information gap at low marginal cost. Our research question is therefore, can we causally identify the productivity and welfare impact of combining climate forecast delivery with agronomic extension training in the high deficit context? Let me explain the design. We randomly 100 village in 4 agroecological zones to one of 4 arms into a 2 by 2 factorial design. Within each zone, we matched village into pair ranked by a pre-Brazilian asset wealth index, and then independently randomized each village to receive climate information service and digital agriculture extension service with equal probability. The 2 by 2 design is central to our contribution. It gives us for clean comparison, says only versus control, there is only versus control, and the combined treatment versus control. Usually, it also allows us to estimate the interaction term beta 3, which directly tests whether the two interventions are complementary. I want to flag 2 methodological choices that distinguish our paper from most in this literature. First, we estimate the long model, including the interaction term, following the recommendation of Michler and co-author in 2023. We showed that the short model without interaction has in flat type 1 error rate when interactions are not zero. In this case, in our truth year result, second, we cluster standard error at the village per level, 80 per rather than the village level, following the Checksman and Ramirez-Keller 2020 result that with village level clustering in paired design can inflate the type 1 error at 2 16.5% for a nominal 5% test. Our approach is more conservative. Let me describe what we actually delivered to treated village. The sales model had 4 components. First, 7-day localized weather forecast sent twice per week during the October to April main season, and once per week in the dry season. These were SMS messages of 160-100 characters, cascaded from ensemble forecast to the district level at about 10 km resolution. Second, monthly seasonal climate outlook delivered via 90-second air voice call based on Madagascar National Meteorological Service forecast incorporating Indian Ocean Sea surface temperature and ENSO data. Third, weekly market price bulletin for rice, maize, and cassava succeed from the National CSAE Marketing Information System. And fourth, event-triggered cyclone, flood, and drought alert, averaging about 6 per year. The DICE model combined digital delivery with fast-to-fast learning. It has 12 structured group training sessions of 3 hours each, covering the full group calendar from soil preparation in September through to climate-smart planning for the next season in May. The sessions were delivered by 24 locally recruited field facilitators trained by MIPE agronomists. Each session was reinforced by a corresponding SMS recap sent within 24 hours. Our data collection consists of 3 main surveys, round plus 4 annual agriculture tracking survey. The baseline round 1 was conducted in October to November 2019 before any treatment delivery within 3,200 households across 160 villages. The Madeline round 2 after the second growing season in October 2021, recovering 96.5% of the baseline sample, and the handling round 3 was conducted in October to December 2023, recovering 93.5%. 2,991 households. In addition, a phone-based tracking survey was administered every April, May to be a random 50% subsample, capturing with seasonal crop management decision and winter shock exposure. The baseline balance table confirms successful randomization. No variable show a statistically significant difference across the 4 arms at the 5% level. The John F. test of all arms specific difference simultaneously being 0 yield and p-value of 0.43. The baseline rice yield of 1.74 ton per hectare is consistent with published estimate for our study zone. Attrition over 5 years is 6.5% at handling, which is comparable to other long-run agriculture ST in sub-Saharan Africa. Let me turn to the main result. I'll estimate use the long model with par-clustered standard error and a free correction using 10,000 randomization permutation. Starting the normal season result shown in green. 6 alone raise irrigated land rice yield by 0.29 ton per hectare, a 17% gain over the control mean of 1.74 ton per hectare. There is alone raise yield by 0.22 ton per hectare, 22%. The combined treatment raise yield by 0.29 51 tons per hectare, 45%. All three effects are significant at the 0.1% level after F3 correction. The interaction coefficient beta 3 is normal season is essentially zero, meaning the combined effect is approximately additive. There is no complementary in the normal winter condition. No, look at the 2 year 2021-2022 shown in red. The season experienced 35 to 45% below normal rainfall in our eastern and northern zone, classified as drought year by Madagascar Meteorological Service. In this year, the combined treatment produced a yield gain of 0.75 tons per hectare, 53%, and crucially, the interaction coefficient beta 3 becomes significantly positive of 0.16 tons per hectare. This is the complementary result in year 6 and days reinforce each other because receiving a drought forecast is much more actionable when you also have the agronomist knowledge of drought-tolerant variety and adjust fertilizer protocol from the day's training. This slide unpacks the mechanism behind the yield effect. The key insight in that is that CSAEs and DAEs operate through entirely different channels. CSAEs affect timing decision. Household receiving winter forecast are 18 percentage points more likely to shift their planting date by at least 5 days in response to the seasonal forecast, and 14 percentage points more likely to plant a drought tolerance variety and drought year. There are information and behavioral change that require no additional knowledge, just access to the forecast. These by context affect input intensity and practice adaptation. These alone raise any mineral fertilizer used by 12.8 percentage point. Fertilizer intensity among users by 8.4 kg per hectare and adaptation of at least 3 recommended agronomic practice by 24.1 percentage point. This effect requires farmers to actually learn and apply knowledge, which is why they depend on the training session rather than just SMS message alone. The combined treatment captures both channels with their focus improve timing and agronomic training improve the input response to those timing decisions. This is the mechanism behind the two-year complementarity. A farmer who receives a drought forecast and has been trained in drought-tolerant variety can act on both places of information simultaneously. Let me turn to who benefit most from the combined treatment. Starting with gender, female-headed household gain 0.67 tons per hectare, a 35.6% increase over the control mean. Male-headed household gain 0.41 tons per hectare, 18%. The trip interaction time size times days times female is 0.26 tons per hectare with a p-value of 0.02, confirming a statistically significant gender differential. On yield, the yield gain follow on a monotonic pattern. The second and third yield quartile benefit most 0.58 and 0.63 tons per hectare respectively. The poorest quartile gains only 0.28 tons per hectare, roughly half the middle quartile. Agronomic advice recommending fertilizer. They lack the working capital to purchase the recommended quantity. Digital literacy also constrains the poorest. They have uptake rate 26 percentage point lower and yield gain 49% smaller than the top literacy quartile. By agroecological zone, effects are largest in the eastern coastal zone, 0.64 tonnes per hectare, and smallest in the central highline, 0.38 tonnes per hectare. This pattern is exactly what we would predict. The east has the highest weather variance, the lowest baseline access to a climate forecast, and the lowest extension coverage. The intervention has the highest impact where the information deficit is deepest. Beyond threshold, the combined treatment generates large welfare improvement. Food insecurity fell by 20 percentage points from 61% in the control arm to 41 to 41% in the combined arm, significant at the 0.1% level after full correction. The household dietary diversity score also improved by 1.3 food groups, suggesting qualitative dietary improvement alongside the reduction in hunger. Children's school enrollment increased by 8.4 percentage points. The effect is larger for girls. 10.9 percentage point, down for boy, 6.2 percentage point. Neither the says only not the dice only arm produce a significant enrollment effect in isolation, suggesting that the schooling gain requires the full income lift from the combined agriculture improvement. The most likely mechanisms are income, relaxing school fee constraints, and reduced demand for yield agriculture labor during peak farming period. Women empowerment measured by we composite score increased by 0.088 standard deviation in the combined arm, primarily driven by the input in productive decision sub-indicator. The cost-benefit picture is compelling. The per household annual program cost at study scale is approximately $90, includes LSMS and either delivery cost facility, salary training of trainer, and monitoring against this. The combined arm generate approximately $87 in additional agricultural income per household per year. The benefit cost ratio is 4.6 to 1 on productivity alone. Let me briefly walk through our robustness check because the credibility of causal claim depend on ruling out key threat. First, spillover, we test whether treated village contaminated neighbor control village by regressing control outcome on proximity to treated village. All coefficients are near 0 with p-value above 0.20. A sub-survey of no control household in control village find their yield are indistinguishable from comparable household in North Studio region. Second, attrition at 6.5% over 5 years. Our attrition is low and balanced across termly bound, confirm the combined yield effect is significantly positive even under the most conservative attrition scenario. Third, this is an important methodological contribution. And let me summarize. This is paper present 5 years experimental evidence from a pre-registered 2x2 factorial RCT in Madagascar. The four substantive findings are: first, climate information service alone raise yield by 17% with much large effect in 2 years. Second, digital extension service alone raise yield by 22% constantly operating through improved fertilizer use and agronomic practice adoption. Third, the combined treatment raise yield by 45% on average and 53% in 2 years, with significant complementary emerging specifically in climatic adverse conditions. Fourth, the combined treatment reduced food insecurity by 20 percentage points, raised children's school enrollment by 8 percentage points, and deliver a benefit cost ratio of at least 4.6 to 1. For policy, our results suggest three priorities. First, multi-channel delivery combining SMS, IVR, and village group training is necessary to reach farmers with low digital literacy. A purely digital approach leaves the most vulnerable behind. Second, equity gap. Third, climate information is most valuable in high variance zone and adverse years, suggesting targeted deployment by agricultural zone. Thank you for your keen attention.
The first and actually the very main question that I have is that your coefficients are really big. It's a really high impact. So it's 22% to 45 yield gain, which is much higher if you compare it to other papers that have used a similar RCT. So how do you explain? I would be interested in knowing how you would explain that. Is it because the baseline education level is really low among farmers, or is it I mean, you did explore drought a lot, so the control group maybe suffers from drought a lot more than the treatment group does. So that's the very main question that I have, or something that you should explore maybe. uh, Secondly, I would like to look into like heterogeneity analysis for how do different education levels, people from different education levels get impacted. You did look into the female and male impacts differently. And similarly, how do you, because it's a study from 2019 to 24, so how do your impacts get affected over time? Do they die out, or do they remain the same or get bigger or whatever? So yeah, those are my two, three main questions.
D'accord. Pour la première question, nous avons fait des préenregistrements des collectes des données avec les baselines là. Donc, nous avons collecté depuis 2019 jusqu'à 2024 et nous avons appliqué le méthode de randomisation de PAC 2. Donc, nous avons appliqué les erreurs clusterisées au niveau des paires des villages. Et nous avons appliqué le FWIR correction pour avoir un équilibre dans ces bases de données-là. Donc, c'est notre propre hypothèse, mais c'est ça nos résultats. Donc, je ne sais pas comment il a été élevé, mais parfois, donc, les agriculteurs utilisent bien les informations, utilisent bien les formations complémentaires. Ça pourrait avoir un impact sur les chiffres là. Et pour la deuxième question aussi?
Yes, so what he say is that he actually did all the process that is needed for the RCT, but that is the result that he get. So he can actually explain why his coefficient are so high. So yes, but all the process that it took place was like respect all the hypotheses and all, but the coefficient are just like that. So yes.
Pour la deuxième question, donc l'impact a été hétérogène parce que les femmes là-bas n'ont pas plus accès à des informations par rapport aux hommes. Donc après la formation là, il y a un impact plus élevé pour les femmes que les hommes parce que les femmes euh, ré- euh, utilisent bien les informations et ils sont beaucoup qui sont quoi là? Sont ils ne se marient pas, mais c'est eux qui, qui fait le truc là. Donc il y a beaucoup de femmes par rapport aux hommes qui sont bien actifs, qui ont bien reçu l'information par rapport aux hommes. C'est pour cela que l'éducation a été plus impact pour les femmes que les hommes. Oui, c'est ça.
Oh, about the heterogeneous effect on the education between the men and the women, he says that the women the women actually use the information more correctly than the men do. So that's why you can explain the diverse or the heterogeneous effect that we can see between the female and the women. So Now it's open. You can discuss after the session. Thank you.
Good morning. My name is Vaishali Jain. I'm a PhD student from University of California, Riverside, and we are talking about 5 decades of climate change and technological change in Indian agriculture. Starting with the motivation, Indian agriculture feeds 1.4 billion people, employs 263 million people, and a lot of it is dependent on monsoons. And as we know, the temperatures are rising. So the obvious question to ask here is if farmers are adapting to climate change. So far, the evidence has been mixed and discouraging for India. 2009 study by Guterres finds no adaptation in India, and also the Burke and Emmerich paper finds very limited evidence of adaptation for US corn. So one of the main research question that I have is how much does extreme heat damage in short run and also in long run, and how do farmers adapt in India? And for this, the main mechanism that I use to show the adaptation is green revolution. So not just the HYV seeds, but the bundle approach of HYV seeds, irrigation share, and fertilizer intensity used on farms. Apart from that, I also look into other mechanisms like how do farmers plant and what crops do they choose over time. So just a preview of the findings, I find that for an increase in 100 extreme degree days, the rice yield reduces by 9.6% and wheat yield reduces by 5.6%. In the long run, I find an evidence of adaptation using the long differences impact. And for green revolution, I find that the HYV seeds variety for rice themselves are more heat tolerant, even when I control for irrigation and for fertilizer. But for wheat, HYV variety seed effect disappears once we control for irrigation. So that is the main adaptation channel. And then I look into other things where I find that cropping intensity actually reduces, diversity actually increases as we have more extreme damages. So the first contribution is that there are very few studies in India looking at a 50-year time period, and again limited evidence. So I do find evidence of adaptation. Green Revolution, I think, is the first paper that looks at the unintended effect of Green Revolution, which was more intended for as a food security and not as a climate policy. And again, the intensive margins is, I think, understudied in India as a mechanism. So this will be the structure I follow. First, two crops. So we have two different seasons. Rice is the monsoon season crop, which runs from June to November, and wheat is the winter crop, which runs from November to March. The climate context, there has been an on average additional 8 extreme degree days if you compare the first decade of my study to the last decade of my study, which is from 1965 to 2015. There's also, so this is temperature exposure across, for both the crops for different decades. So as you can see for the left side, rice, you can see there's a clear rightward shift. So temperature has been rising for, especially for rice growing season. For wheat, I don't see that kind of a very prominent impact, but on average. There's a lot of spatial heterogeneity as well. So this graph, this heat map really shows the difference in the number of hot days between the last period of my study compared to the first period. So the red shows the warming up of the districts, and the blue shows is basically number of hot days have actually reduced. So as we can see, it's mostly concentrated on northwestern side. India does see the number of hot days increasing, and then in the south we have some blue districts. For wheat, it's more dispersed. So origin, I don't want to go to a lot of detail, but it basically started in 1965, and they started adopting this technology wherever they had irrigation infrastructure in place. but it rapidly got adopted in the next 20 years. The main data source is ICRISAT in India. This has 50 years of data, which is harmonized in the 1965 district borders, so we don't have to worry about more districts being created in the 50 years. So this is where all the agricultural data comes from, the climate data comes from ERA 5, and using this hourly temperature data, I will be creating two variables. The first one is the moderate degree days, which is like the beneficial range, so cumulative degrees between 10 degrees and the damaging threshold. And the second one is the extreme degree days, which is cumulative degrees across the damaging, after the damaging threshold. So before we move on to the regressions, we will start with identifying this damaging threshold. For rice, for both the crops, I actually create these 3-degree bins, and then I try to find out at which bin does the yield start going negative. So how is it related to the higher temperatures? For rice, I identify 33-degree as the damaging threshold, because before that, it's mostly either stable or very close to zero. And for wheat, I identify 30 degrees as the damaging threshold, but I do check different thresholds in the robustness checks, and it doesn't matter a lot. Uh, Going to the empirical strategy, we have a very standard panel fixed effects model where I have MDD, EDD, which is the main two variables, and the other controls are precipitation, precipitation square, state trend square, and district fixed effects. Then we move on to the long differences impact, which is basically showing you the long run adaptation story. In the green revolution, I will be interacting the EDD, which is the extreme degree days, with the HYV variety share to find out if does it moderate any negative impact. And in heterogeneity test, if we have time, we can go over. But I will again be looking at the interaction terms. So sorry. So this is the main table that I have for rice. These are just year-to-year variations, and how does rice yield and production get affected because of extreme degree days. And as you can see, an extra 100-degree days reduces the yield by 9.6%, which translates to 3.4 annual loss, because the mean EDD is 35. And for production, again, for both the crops, we see more higher impacts. So I'll be discussing the area part also later. But for wheat also, again, we see a negative impact, which is slightly lower, but again, we do have a negative impact. For MDD, rice, we see a positive impact because it's that beneficial threshold between 10 and 33, where it's actually very beneficial to the yield. And for wheat, we do not see an impact, or it's negative slightly, which is, I don't know how to explain that, but it's a winter crop, so we can expect this, right? So long differences. What is long differences? We compare usually panel fixed effects with long differences. It's the same thing as panel fixed effects, but it's not year to year, it's decade to decade. So we are averaging out the yield and the climate variables for one decade, and then again averaging out for the last decade, and then we subtract them and compare them. If we see that districts that are warming up have worse yield, then we can say that there has not been an adaptation. But over here, I try a lot of combination and a lot of different windows for 30-year difference or 40-year difference, and I do not see any effect. For some of them, it's positive. For some of them, it's negative. But compared to the year-to-year fixed effects, which is 9.6 minus 9.6%, all of these effects go down to zero. But we should note that the standard errors are large. So again, with caution, maybe we can say this. So the first mechanism that I look at, the most important one which I look at, is green revolution. The first is the baseline model, which is just the panel fixed effects we just saw. But if you notice, the number of districts have gone down a lot. That's because of the data which is available for Green Revolution. It's not a lot of data, so I had to limit the number of states I had. But these 84 districts, they represent about 75% of the total Indian production for rice and also for wheat later. So we start with baseline. The second column is where we interact the HYV area under rice with EDD, and we see a positive coefficient of 4.1 percentage point, which is positive. So we can see that actually HYVC does reduce the heat stress. The third one is really important because that's where we control for irrigation share and NPK intensities, just fertilizers. And we see all of these inputs are important, but the interaction term does not reduce a lot. So the HYV seeds still remain important even when we control for other inputs. The fourth one is really the full interaction. It has interactions with irrigation and with fertilizer in the same equation. And again, we see that we don't find anything significant for the other inputs. And the main interaction still remains to be EDD by HYV, where we see that the net effect will be minus 7.7% instead of the really high 14.6%. Okay, because of the HYV adoption. So for rice, HYV seeds seem to really matter. For wheat, this changes a lot. So again, we start with the baseline model. Then we move on to the first interaction term. And it's really huge. It's 7.45%. So it's quite big. And once we control in the third specification, this reduces to like half. So irrigation has a really high coefficient, if you notice, and fertilizer is also significant. But once we have all the interaction terms, the significance for HYV actually goes away. So irrigation seems to be the driving factor for the second equation, because HYV area, irrigation, fertilizer, all of these are correlated. So once you control for irrigation, the HYV alone does not seem to matter. So for wheat, which is a dry season crop, actually irrigation seems to matter a lot. Yeah. So apart from yield, I also look at other outcome variables. One of this are cropping intensity. So how many times does a farmer grow on the same piece of land? I find in case of an extreme heat event, that cropping intensity or multiple cropping actually reduces. And in case of MDD, we have a positive. So exactly the opposite effect. Log gross cropped area is the total land area. So it can be counted, a land can be counted twice if it's sown twice. So again, that's negative for the extreme degree days and positive for MDD. And for fallow land also, the land the fallow land increases because of EDD. So this is how they the crop portfolio choice how they make the crop portfolio choices. For wheat, I find that actually the farmers shift away from wheat whenever there's an extreme event in the previous year. So if it's a hot year previous year, this year they will plant away from wheat. For oil seeds and for pulses or lentils, it actually increases. So, so we can say that oil seeds and pulses are more heat resilient crops. So they are shifting towards these two crops. And for rice, interestingly, I do not see any impact at all. Crop diversity also increases when there's an extreme heat in the previous year. So that follows the literature. Okay, so these are some of the additional results. I basically split the districts into different categories. Either they are warming up, so remember seeing the red districts and the blue districts. So I want to find out if the warming districts are differentially impacted. Then I look at other different heterogeneity factors like the baseline temperatures. So the hot districts, are they differentially impacted, or irrigation, basically, if you have higher than median irrigation in the first decade, are you differentially impacted, and so on. So for that, I find out that, so this is just baseline. For rice, it does not seem to matter a lot for the baseline temperature and for irrigation, but just the warming districts, basically the districts that were red, do fare worse than, okay, thank you. So heat sensitivity is very uniform across all the districts, but if we can see that for the warming districts, the districts that were red actually have worse impacts. So again, I should. Okay. So for wheat, we actually do find some results where if you compare the first column, which is the z equal to 0. So basically that 0 and 1, the third column. So districts that have a higher baseline temperature compared to districts that don't. So we do see that there are some, the warming up districts, the red districts do seem to have a higher ADD impact, which is consistent with the Green Revolution story. Okay, and yeah, okay, I think I don't want to go into that. Okay, so I can just conclude over here. The short run damage, we saw that in the short run, the rice and wheat do get affected with yield losses and even bigger production losses. In the long run, I find effects on yield. I don't find effects on yield or rice, which I interpret them in comparison to panel fixed effects as an evidence of adaptation. And then I look into different mechanisms. And for rice, I find that HYV seeds variety of rice themselves are more heat tolerant, and they seem to play a more important role than even irrigation and fertilizers. And for wheat, it's more, the adaptation is through irrigation. Apart from that, we looked at other different extensive margin results where the farmers tend to reduce the cropping intensity and increase the wheat share into other heat tolerant crops like oilseed and lentils, and they also tend to diversify more. So the policy implication for that is that we need differential policies for different crops based on their adaptation strategy.
Thanks. This was a very enjoyable paper to read. A lot of work. And yeah, I mean, I don't have many comments. It was very polished. Couple points, at least, and I didn't get any clarification here. There's that initial graph that you show that has the effects, the yield effects at different temperature bins. And most of them seem to have zero effect. And then when you get to kind of your second to last slide, you have these, 9.5% reductions, which I guess just comes as a surprise after it seems like heat doesn't really play that much a role. And then when you move to the next regressions, then suddenly it just has a larger effect than I would have expected. Like 10% decline seems really large when across the board, heat doesn't seem to have that big of an effect. In terms of no effect on the long differences, it may be adaptation, or you may just, when you do the long differences, you're eating up so much temporal variation that, temperature doesn't matter anymore just because you're eating it up with the long differences. So it could just be, that could be the reason why there's a null effect. As you mentioned in the presentation, irrigation and HYV adoption are highly correlated. So if you checked the variance inflation factor, the VIF, to see like how correlated they are and if that's causing any problems in how the estimator distributes the effect between HYV adoption versus irrigation adoption. And then finally, I had questions about measurement error. ICRISAT spends a lot of time in and around Hyderabad, and where they were the VLS VDSA villages that they started collecting data from in the 1970s. So I'm wondering, are there district level, do we have a reason to think or be concerned about differential measurement issues, that the measurement of HYV adoption and yields in the districts in central India where ICRISAT had its most intensive work are going to be different than, it's going to be noisier when you get further away. Also, rice isn't a ICRISAT crop, so are they paying less attention to rice? There might be nothing there, but it's an interesting thing to think about is like, could that be some of what's driving it? There's just better data in those areas, and so it's less noisy, and that's why you're getting these big effects, especially when you go to just the HYV districts. Thanks.
So starting with the measurement error, as far as I know, ICRISAT actually compiles all of this data. There are state documents, and they just compile it for each district. So they're not first-hand collecting it like the VLDSA data that you mentioned. So yes, I mean, it depends on what kind of state it is. There are certain states, especially the northern ones, which report almost all of the data. And then for certain states like Bihar, there's a lot of data which is missing, so I have to drop them. So certainly there is always an issue for measurement error. That I acknowledge. For the long differences, yes, the standard errors are huge. I don't know what to do about them. I tried a lot of different windows and a lot of different time periods, but the thing is, my number of districts is just 260, about 260 for rice and wheat. So I think I don't get enough power over there. So I don't see anything over there. The other thing about the coefficient that you mentioned about the 9.6 percentage point, so it's actually 10 times smaller than a lot of other papers, if you see Burke and Emmerich and other papers. So I do look at the heterogeneity by like different growth stage. I don't know if you have this. Yeah, so this is how it should be. They should be 10 times bigger. But when I look at them by the growing stage of the crop, so I start with the vegetative state, which is when the crop is just a seed, they're just germinating. Reproductive, when it becomes slightly bigger, and green filling is when they are like full flower. So if you look at that by stage, the coefficients do go up, but yeah, so this is, I don't know, we can maybe discuss later. I forgot what the second question was, I'm sorry.
Correlation.
Oh yeah, the correlation, yes, the correlation is there. I don't know if I have the correlation matrix over here. I don't have it. But even when I look at the interaction terms, just the interaction terms of fertilizers with EDD or irrigation with EDD, I find very consistent story. But yeah, definitely all of these measures are correlated. And in northern states like Haryana and Punjab, you will find higher irrigation, a better irrigation infrastructure, and higher HYV adoption. So all of these things are correlated. So obviously we need to take this with a grain of salt. But yeah, that's it. Any other questions? Yes. Yes, anyone.
Okay, I also thank for the nice presentation and interesting paper. So you told us about the adverse effect of climate change on yield in crops. But there are also some studies that indicate climate change does also have some positive effect on yield through carbon fertilization. So, I mean, wouldn't it be possible to consider this point as well? Because if there are possibilities for carbon fertilization, then your result may appear a bit overstated. That could, including this issue, could perhaps result in certain, to some extent, lower yield effect. Thank you.
Okay, I haven't looked into the positive effects of climate change a lot, but yeah, there is certainly a chance that it will happen. Maybe that's why I don't see any impact on long differences, because a lot of way too many variables at play. So yeah, I mean, I should definitely include it if I can maybe even find the data of yeah, please. Thank you.
I want to suggest maybe a framing issue that in some of the old sort of stories that used to be told about the Green Revolution crops was that they had higher yield but higher variance, and so they weren't going to do well in these sort of extremes. And this is sort of what you still hear in like geography and anthropology. Discussions about Green Revolution. And it seems like your results are actually quite strongly suggest that they are more robust to these to climate change. And I think that's a really important finding beyond just, oh, is it a 10% drop due to EDD or whatever, that being able to show that the Green Revolution crops have actually made these places much more climate resilient. It seems like your results show that actually there's relatively little effect compared to the rest of the literature. So I'd encourage you to think about framing it around what did the Green Revolution do?
So in terms of, okay, so you're saying that there is a possibility that it does not actually play a role in any kind of moderation of climate change, or I don't know how to could you repeat that point?
What I saw in your results is that the Green Revolution crops are really important in moderating climate change in India. Is that
Yes.
is that
Yeah.
correct?
Yeah. For
Okay.
rice, especially, I find that impact. Yes. But it definitely is still a bundle effect, like irrigation and fertilizers, they together, because irrigation plays a huge role in case of wheat, surprisingly. Yeah, it's definitely a bundle effect, I would say. It's not just the HYV seeds themselves. So, yeah.
Right. I guess, but I guess my thought is that the early literature on this suggested that Green Revolution or that bundle tended to be higher variance, higher mean, higher variance.
Okay.
And you're suggesting that it is higher mean, lower variance.
Okay.
Which is a very different story.
Okay.
And I think
Yeah.
the old story exists in a lot of sort of academic locations,
Okay.
at least.
So maybe an analysis by decade might impact, like with different adoption rates. Because the thing is, my study is very concentrated in districts that have really high adoption rate, which reported a lot of data. So it didn't have any missing data. So yes, I definitely I understand your point that maybe southern states which didn't adopt a lot, maybe there's a possibility that those were differentially impacted.
This is a paper we're calling a very long title, Variable Selection in Socioeconomic Applications of Remotely Sensed Weather Data. It's work with Talip Kilic at the World Bank, Anna Josephson, and a former grad student who's now at Cornell. So as you'll see at this conference, we as economists use remotely sensed weather data quite a bit. And it's still very common to use remotely sensed weather data as an instrumental variable when you're trying to isolate some sort of causal impact. This graphic is from an excellent paper by Jonathan Mellon called Rain, Rain, Go Away. I highly suggest everyone reads it. He reads 289 papers that use rainfall as an IV and shows how rainfall is used as an instrument for all of these different things. And if we're using this as an instrument for all these different things, that implies there are exclusion restrictions in some papers that are being violated. And so what we're doing is similar to what Jonathan did, but we're going to use LSMS data and basically run a bunch of first stage regressions in which we regress yield on different measures of rainfall to see how do our estimates change as we change the sources of the rainfall data and as we change the way we quantify rainfall. Right. So this is, again, building on Melon's figure on the previous slide. We use rainfall to instrument lots of different things, and we use different measures of rainfall. So Banerjee and Iyer use mean total rainfall as an instrument for egg production. Hughes uses mean monthly rainfall. Is one of them better than the other? Is one of them right agronomically? Or are these both substitutes and we can use either metric as an instrument? Same with health and nutrition. Some use deviations in total rainfall, others use the log of rainfall. Are they substitutes for each other, or is one of them nutritionally more appropriate than the other? We do this in a lot of, we do this in a very ad hoc way. Very few papers that I read justify why they choose this specific measure of rainfall or temperature, the last paper accepting. Having it up here is really annoying. So the fact that we use these so the fact that we use all these different metrics implies that we may have these exclusion restriction violations, and the fact that we use so many different ways to quantify rainfall implies that maybe there's some sort of selective inference, that we're choosing one rainfall measure not because it's the reason the one we should be using, but because it happens to be important in our case, or like it gives us the result that we want. So our goal in this paper, in a series of papers that Talip, Ann, and I have written, is to provide researchers with some insight about which variable you might want to choose if you're going to use rainfall as an IV. The first thing we're going to do is we're going to train a generative AI model, ChatGPT, to read a bunch of papers in economics that use rainfall as an IV to try and quantify or document the ad hoc nature of the way that people use instruments. And then we're going to run a bunch of regressions in which we regress yield data from the LSMS on different metrics of rainfall to see how our results change as we change the source of the data and as we change the way we quantify rainfall. Okay. So to do this AI literature review, we go to a academic database called OpenAlex, which has 456 million scholarly works. We search for the universe of papers that use rainfall or weather as an instrument. This gives us about 3,756 papers. Obviously, I guess I could pay a grad student to read 3,756 papers, but that'd be a long time. So what we do is we read about 10% of them and label them what the IV is, if they use an IV, what the dependent variable is, what the endogenous variable is, if they use an instrument as their way to identify an effect. And so we take that basically labeled data, about 400 papers, and we use that as a training data set in a kind of classic machine learning approach, where we split it into 70% training, 10% validation, and then we hold 20% out as our out-of-sample test. So once we've trained the model, then we'll have it read all 3,756 papers. And so we ask it to extract information that's just binary. Is it an empirical paper? Yes or no. Does it use an IV? Yes or no. Is the IV rainfall? Yes or no. And then what's challenging for generative AI models still is to extract actual specific content. So we ask, well, what is the endogenous variable? What is the rainfall variable? It's important to note that we're not actually training ChatGPT. OpenAI doesn't allow you to change the weights in the model, but what we're doing is training it, and when we're training it, it creates these adapter matrices which move or kind of adjust the weights that exist in the GPT model. So what are our results? Or how effective is GPT at rating papers? It's very effective if you just ask it yes or no questions. So these are confusion matrices based on our results. And so 93% of the time, it gets it right when we ask it, is the paper an empirical paper or not? when you ask it, does it have an IV, yes or no, it's again fairly accurate 90% of the time, and it's pretty precise. So it performs well when when we're asking it to ID if an IV is used. When we ask it, does it use rainfall as an IV, it has high precision. It gets, does this work? No. 23% of the time, if it's a true zero, it reports a zero, no rainfall IV. 34% of the time, if there's a rainfall IV, it identifies it. But you see this 40% of the time, so it has low sensitivity. 40% of the time, there's a rainfall IV that it's not flagging. And so it's, it tends to be, it's pretty good at finding these things, but there's a lot of rainfall IV papers that it's missing. When it comes to actually extracting strings of data, so what is the rainfall IV? Its performance is pretty poor. 46% of the time it gets it right. Now we have to use BERT semantic similarities, and so some of the issue is it might get pretty close, but not close enough for the semantic similarity match to identify it as a match. Having trained the model to this degree of accuracy, then we release it on all 3,756 papers and ask it to map what the rainfall IV was and what is it instrumenting. And you get a Sankey diagram like this. So on the left-hand side are all the different ways that these papers quantify rainfall. On the right-hand side is all the different things that rainfall instruments. And so you can see this sort of wild and woolly way that we as economists use rainfall as an instrument. We quantify rainfall in numerous different ways. Sometimes they're means, sometimes they're totals, sometimes they're deviations, sometimes it's the variance, sometimes we're just counting up the rainfall days, and then we use these things to instrument for whatever we want. Give me a variable, tell me it's endogenous, I got a rainfall instrument for you. So this suggests, like this suggests, like Jonathan Mellon's paper, that there's a number of papers out there that have exclusion restriction violations because these things on the right over here, these are correlated. And so if we're using if the exclusion restriction is that rainfall only affects egg production, but egg production is correlated with migration, and then someone else is using rainfall to instrument for migration, one of those papers has an exclusion restriction violation. I don't know which one, but one of them does. Just that's how exclusion restriction works. So going then to the LSMS, we use all 6 LSMS countries. We're going to pull rainfall data from 6 different weather products: ARC2, CHIRPS, ERA5, MER2, TAMSAT, CPC, and we're going to generate 14 different ways to quantify rainfall. Mean, median, variance, skew, number of rainy days, deviations from long-run average, longest dry spell. We're going to regress either value of harvest or quantity of maize on this rainfall variable in the way that you would in a first stage regression. And then we're also going to include just weather only. We're going to include household fixed effects, and we're also going to include inputs. And so the idea is to mimic a first stage regression in which you think agricultural yield is endogenous and you want to use rainfall to instrument for that. As I said, we're going to use just weather only. We're going to include fixed effects, and we're going to include inputs. And we're going to see how do our results change as we change the source of the weather data and as we change the way that we quantify weather. All right. Before we get there, we're going to look at so we run 3,000 regressions. And so we take all the p-values on the rainfall variable, and we just figure out what share of coefficients are significant of those 3,000 regressions. And so you see, when we only use weather, no fixed effects, no inputs, rainfall highly correlated with agricultural production. It's great. As soon as we put fixed effects in there, goes away. Rainfall has no impact on agricultural production once you include fixed effects. Add inputs doesn't really change anything, but rainfall, any measure of rainfall, highly correlated with agricultural yields until you account for household fixed effects. 85% of rainfall metrics are significant. or 80% of the time, 85% of the time they're significant, this would say, oh, this is a relevant IV. I found a good instrument for agricultural yields. Problem is, we also want to include household fixed effects because we know without including household fixed effects, there's a lot of heterogeneity, a lot of unobserved things that are going on that are going to create endogeneity problems. So we have a relevant instrument when we don't include household fixed effects, but we're not satisfying the exclusion restriction when we do that. As soon as we include household fixed effects, now we've satisfied the exclusion restriction, but now we have a weak instrument problem. Rainfall is no longer relevant to egg production, and so it would be a weak instrument. So there's this trade-off between satisfying the exogeneity requirement of rainfall as an instrument and the relevance of rainfall as an instrument. And so that's something that we need as a group of economists need to think more about and grapple with, especially in cases where we do want to use rainfall as an instrument. All right, then I'm going to show you 3,000 regressions. Here's the results. So I'm going to divide them up by country. On the left-hand side, this is a specification chart. On the left-hand side is what identifies the regressions. The way we're quantifying rainfall, the source of the remote sensing product, and what the left-hand side is, whether it's value or quantity. Okay. So the dots along the graph show you which regression we're using. So if the dot is at deviation of percent rainfall, that's the rainfall instrument, and then it's coming from MER2, and it's using quantity. So you can pick out any specific regression on this chart. What's important is the pattern that you observe. Some regressions, rainfall is negatively correlated. Some regressions is positively correlated within the same rainfall metric. So if I choose deviation percent rainy days, that reduces yield. Makes sense. But if I choose that measure from a different satellite, it now suddenly increases yield. So basically, I can get whatever result I want by judiciously choosing the way I'm quantifying rainfall and the product that I'm using. If I want things to be positively correlated, I can choose one. If I want them negatively correlated, I can choose one. This is not just true for Ethiopia. It's true for Malawi. It's true for Niger. True for Nigeria. True for Tanzania. True for Uganda. Tanzania, rainfall almost never matters. Look at all those black diamonds are all not significant results. Very rarely does rainfall seem to have an effect on Tanzanian agriculture. Guess they don't need rain. Uganda, it often matters. Almost all of these are significant. So many of them over here, negative and significant. A lot of them over there, positive and significant. Again, if you want things to be positively correlated, if you want things negatively correlated, if you want things significant, not significant, you can choose which results you want by switching up the way you quantify rainfall and the source of your rainfall data. So we do see some consistency within countries. So mean, median, total, and deviation are strong predictors in Ethiopia. They tend to be, they're almost always positive if they are significant. And so this says those would be good IVs to choose if you're trying to instrument for something in agriculture. Malawi, there's very few, only skew in rainy days. Niger, almost all of them matter. In Nigeria, only median is a consistently strong predictor. In Tanzania, as I said, they don't need rainfall to grow crops. Uganda, almost everything is significant. The results change by source of product. All of these remote sensing products are ostensibly measuring an objective fact. How much rain fell in a given place on a given day is an objective fact. If we had a rain gauge there, we could measure it and we would know the truth. All of those remote sensing products are trying to estimate what that objective fact is. They should all give us about the same result. They do not. Error 5 switches signs in Ethiopia. If I use mean daily rainfall, error 5 makes crops grow. Rainfall is measured by error 5, makes crops grow. But when I switch to Niger, rainfall measured by Error 5 kills crops. They differ on how much rain they're reporting, and they differ on the quality of data in given locations. In areas that have fewer stations, actual weather met stations, these products do worse. They have higher variance. They are less significantly correlated with yield. So the choice of rainfall product, where you get your data, is not is an important consideration, something that needs to be justified, because your results may be a function not of an actual effect, but a function of your choice of rainfall product. So, wrapping up. We see a large heterogeneity in the way that these metrics perform across remote sensing products and across countries. We see that very few of these metrics are substitutes. In the first couple slides, I showed you how some people are using this measure of rainfall to instrument for ag productivity or health, and someone's using a different one. We can only do that if those things are actually substitutes. But we find that very few of these metrics are substitutable. Sometimes total rainfall will give you positive, and mean daily rainfall will give you a negative effect, right? That shouldn't be the case. But when given the measurement error that exists in these remote sensing products, that's what happens. And so there's this inconsistency across metrics, means that we can't just freely interchange one quantification for another. That means it's a choice that researchers get to make how they choose to quantify rainfall, and it's a choice that needs to be justified in papers. Why are you choosing this metric over another? There's also this exogeneity relevancy trade-off. When we don't include fixed effects, rainfall is a strong predictor. As soon as we include fixed effects, that effect goes away. And so again, we end up with either an exclusion restriction violation or a weak instrument problem. The fact that there's so much heterogeneity in these results, that basically I can find positive relationships or negative relationships based on how I quantify rainfall and which product I choose, means that there's a lot of degrees of freedom we have as researchers. So if I read a paper that doesn't just strongly justify why it chose this product versus another product, or this quantification of rainfall versus another quantification of rainfall, it raises the question, well, did you choose it because that's the agronomically or nutritionally appropriate method, or did you choose it because it gave you the results you want, right? An unethical researcher could choose rainfall from chirps, run the regression, not find the result they want, then go and choose error 5, run the regression, they get the result that they want. So there's a lot of ways that we can use remotely sensed rainfall data to cheat if we choose. So how to avoid doing that? Well, one, you should just be cautious if you're going to use rainfall as an instrument, because there's multiple different causal pathways. If someone's using it as an instrument for yield, and then you're using it as an instrument for migration, well, we've shown that migration changes in yield affect migration, and so it can't be a valid instrument for both of those measures. It can only be a valid instrument for one. And are you the one who gets to use the valid instrument, or is it someone else? You need to justify why you're choosing a specific rainfall metric, and you need to justify why you're using that remotely sensed product, right? Be good to check the robustness of your results against multiple products. And you need to explicitly discuss these trade-offs between the exogeneity and the strength of an instrument. And so in the IV case, we as researchers need to grapple with that trade-off that exists, even if you're just using instrument for a control or interacting that instrument with, say, high-yielding variety adoption. We need to justify why we're choosing that way we're quantifying rainfall, and we need to check, is it just an artifact of MERA 5 or chirps, or do we get consistent results across product?
So thank you very much, Jeffrey, for the great presentation. It was truly a pleasure to read your paper, and I would encourage everybody to read it. You gotta love a good methods paper, and thank you for all the hard data work that you've done. So I have some rather broad comments and then some minor ones that we can talk about later maybe. So first of all, regarding your contribution to the literature, I felt like you were selling yourself a bit short there. I felt like you could link it more to meta-science literature, the general discussion about the replication crisis and robustness and so on. And there's also some other people doing similar things on land ruggedness, IVs, for example. Then some further details on the study selection process for your systematic search would be nice, like a flowchart of when did which number of studies sort of leave your sample and why. I think that would be super helpful. And then for me, the systematic literature search was slightly disconnected from the empirical analysis. So for me, maybe something that connected better, like showing in how far the papers in your sample actually do the things that you're recommending, like trying out different remote sensing products or providing justification for their choice of the rainfall metric. I think that could be super nice. If there's not enough information in the papers, maybe an author survey could help here. And then second of all, I love the specification curves. For me, I think I would just want more. I find your results super interesting, and it would be nice to see also how magnitudes actually change for the two outcomes, like the value of production and the yields look like, and if you could disaggregate that by the rainfall metric, and then maybe a table with your main results would also be cool. And then lastly, regarding the solutions and sort of the way forward, what you're recommending. So apart from checking the robustness across different remote sensing products or sources, sort of what else can we do besides maybe justifying our metric? And sort of, are you able to provide more general recommendations on choosing the right rainfall metric? And how can we include maybe expert advice from meteorologists, geologists, and so on the choice of rainfall metric? Because it also, of course, depends on the context and also on the research question. So sometimes the median or the deviation just doesn't make sense for the question that I'm looking at. So it would be great to maybe include that in the paper. And then lastly, I was wondering whether this is a very specific problem to weather remote sensing data, or whether this could also apply then to, like your colleagues' work on harvest remote sensing data, or for example, greenness and so on and so forth. So thank you very much.
Thank you. I think this is an interesting point to engage and discuss. I have two clarifications. First is the way probably the people, set the data. I wonder whether you have done different simulations to see how the differences across different data sets that you have used on the rainfall. And then on the other side, you just show that when you include the household fixed effect, the result disappear. But I don't know what type of household fixed effect that you use. Is it most on household level or on the farm characteristics? I'm just wondering whether we are talking about the production is mostly from the farm. There's topography, there is a local, characteristics of where the farm is coming from, which eventually is different from one area to another. Is it, I wanted clarifications on what you mean household fixed effect. Thank you.
So I'll follow up with you about the simulations. That's an interesting idea. For the household fixed effects, we're just demeaning the data based on household, right? So we're not putting in dummies for every household. We're just using XT-reg and INS data. Yep. You got to look at your slides.
Well, thanks a lot for this work, because I've spent decades trying to get rainfall to grow crops in data sets and never succeeded. And so, you know, maybe I had the wrong product. I think, but I think you should think about the. This validates all of my failures, so thank you. Um, I think you might think about the qualities of these products in that, I mean, it seems like one potential solution is we need a lot more rain gauges. I remember looking at this in Mali, and there were, you know, 20 or 30 rain gauges that were being used in like the creation of chirps. And that suggests that maybe all these products are reasonably good near a rain gauge and maybe are not elsewhere. And so then we could say, okay, you can use these if your data is near a rain gauge, but if it's not, it's going to be all over the map. But I think I'd encourage you to think about how to engage with the products themselves and the people who've created them, or you know, the scientists who created them, because they're, you know, these are simulation models, right? And it's, I guess the other thing to think about is whether this is mostly true for African countries where there are not many rain gauges, and if you did this, say, in the U.S., where there's a rain gauge every whatever 2 kilometers, that you might these things, they might, all the models might be accurate or more accurate.
Thanks. My time's up. I would love to answer all your questions. C. Josephson et al. It came out in JDE last month for the differences in remote sensing products, and it is very much a low-income global south problem. If I do this in the U.S., it's not a problem. There's rain gauges everywhere, so it's an issue of the sparsity of rain gauges.
Our study investigates how the severity of a weather shock affects farmers' crop production and rural livelihoods. And so instead of looking at a weather shock, specifically a drought, as sort of a binary shock, we really look at the severity, and we want to see how it shapes their plans for weather and climate adaptation and their implemented strategies. So, as you all know, smallholder farmers in sub-Saharan Africa are particularly vulnerable to climate variability due to their reliance on rain-fed agriculture, and due to climate change, weather shocks such as droughts, floods, typhoons, and so on are projected to become more frequent and intensify, and this will lead to productivity and income shocks. The exact impacts that we're going to see depend on the interaction of the weather shock severity and the exposure, vulnerability, adaptive capacity, and response of the poor, of course. And amongst many other factors, for example, the availability of alternative income sources for these farmers, their wealth level, beliefs, and prior experience with such weather shocks actually shape their adaptive capacity and response. So, as I already said, there is already a vast literature looking at adverse weather shocks generally, showing that they reduce productivity and output, and droughts in particular have been shown to increase labor investment in agriculture and poverty levels, reduce consumption and food security, as well as livestock holdings and rural economic stability, whilst farmers have a variety of areas wherein they could adapt. For example, through agricultural technologies and techniques, financial tools such as savings, credit, and insurance. They could invest in other income sources or use migration. However, the literature also shows that adaptation through agriculture might only be a good solution in the short term, and in the long term, more structural and transformational approaches are needed. Furthermore, farmers' adaptation is quite constrained by a variety of factors, such as credit frictions, restrictive gender norms, aversion to experimentation, a lack of infrastructure, wrong beliefs, and information barriers, for example. So the context of our study is northern Ghana, which is characterized by a hot and dry climate. They have one rainy season, We're going to be specifically focusing on soybean cultivation. Soybean is an interesting crop in particular because it's a bit more adapted to drought-prone areas and well suitable for rain-fed agriculture. And the typical cultivation cycle for soybean goes from June till the end of September. So this is the relevant period that we're going to be looking at. And in 2024, a drought occurred that predominantly affected northern Ghana. It was quite special because it was also missed by weather forecasts, which predicted a rather normal start of the rains, but they came late. And there was also lower rainfall volume. On the right-hand side, you see a map of Ghana, and highlighted are the 4 regions that our study takes place in. So where does our data come from? We collected data ourselves from a sample of 1,354 farmers. They're organized into 78 farmer groups living in 17 soybean growing communities. And these communities, as you see on the right side, are dispersed across the 4 regions. We sampled these farmers through an agri-tech company called Vamiagro that works in Ghana, because this was originally intended to be an RCT, which could not be implemented due to the drought. We did 3 survey waves, one just before the drought happened in June 2024, before the planting, and then the follow-up survey came just after the drought and after the harvest in January, February 2025. This year, last month actually, we went back and did a second follow-up survey, but the analysis will mainly focus on the first 2 survey waves. And we match that with satellite rainfall data, of course, that we obtained from the NASA. It's called the iMERGE data, and it comes in 10 by 10 kilometer grid cells. We actually chose this data source based on the literature. And we created our measure of drought severity by taking the 10-year average of seasonal rainfall from June to September, and from that we subtract the rain that fell in 2024 also from June to September and scaled it by the standard deviation. We did that because 10 years is a classic period also in the literature and a relevant period for farmers. This is what we heard sort of from discussions with people there. And on the right-hand side, you see a graphic showing the variation we have in our drought severity measure. So positive values here indicate a lack of rain or more severe drought. We do 2 estimations. The first one is a difference in difference estimation, in which we include a time dummy post, and then we interact that also with our measure of drought severity that, as I showed you, varies on the community level. We include household fixed effects, and we cluster standard errors at the community level. Because we only have 17 clusters, we make inference based on p-values from the wild cluster bootstrap. And to look at adaptation, we only added a few more questions to our survey for the first follow-up survey. And so we have to look at this cross-sectionally. All of the outcomes are going to be dummies, where we regress our dummy if a farmer adapted through a certain type of strategy on drought severity, and we include a set of individual, household, and community level controls, such as age, gender, education, household size, and an index of infrastructure availability. We do not interpret this as causal evidence. Of course, this is more of a descriptive analysis, because we cannot be sure that we're really controlling for everything here. So let's go to our results. And before I really jump into that, a short note on our tables. As I said, we are making inference based on the wild cluster bootstrap. So in parentheses, I'm showing you p-values based on the regular clustered standard errors, and in brackets, you're seeing the p-values based on the wild cluster bootstrap. So just so you're not confused. And let's start off by looking at yields for soybean and revenue, and then also revenues from all other crops. Because a lot of farmers actually were not able to plant and had 0 yields, or Some actually just their harvest completely failed. We do this as a twofold exercise and first look at the extensive margin and the probability that a farmer actually has any positive yield and revenue. In the first row, we see that generally the effects point into a negative direction, that they had fewer or a lower probability of having any yield or revenues in the drought year. But the effects are not statistically significant. And then we see an additional decline with a 1 standard deviation increase in drought severity in the likelihood of having any positive soybean yield by 21.3 percentage points. We also see, if we focus now on the intensive margin, that those who actually had positive soybean yields suffered yield declines with increasing drought severity of about 19% when drought severity is higher by 1 standard deviation. We don't see any effects for the revenue. They're not significant, but we see also a strong negative impact on the revenue from other crops of 33% with a 1 standard deviation increase in drought severity. This shows us that while the drought was all over northern Ghana, some areas were more severely affected in terms of their agricultural productivity. Let's look a bit at inputs, and now I'm only going to talk about soybean production. So we see some impacts on labor demand, actually. With a 1 standard deviation increase in drought severity, farmers were less likely to hire any labor for land preparation and planting by 17 percentage points. And also for harvesting and threshing, they had a lower likelihood also by 9 percentage points. They also significantly reduced the number of workers by more than 1 worker in each of those 2 phases. And if we compare that to the average number of workers hired in the pre-drought year, that constitutes about a 30 to 50% decline in labor hired. And we do not see any substitution of hired labor through family labor, for example. The effects we see for total input costs are similar in magnitude, but they're actually not statistically significant. We also did a heterogeneity analysis to see whether, for example, women, less educated farmers, and poorer farmers are more adversely affected by the drought. However, we do not see any significant differences across those socioeconomic groups. And then as an additional heterogeneity analysis, we also looked at whether farmers who use their phones to obtain agricultural information, like weather forecasts and advice from extension officers, for example, make different decisions, because this is also what the literature on phones and their significance for agriculture shows. We see that they do make somewhat different input decisions. They're more likely to purchase drought-resistant seeds and hire more labor. But they do not seem to be better shielded against the drought because we see no differences in yield and revenue outcomes. So after we've established that agricultural production is negatively affected, let's also look a bit at farmers' income portfolios as households. So in this table, all outcomes are dummy variables indicating whether this type of activity is one of the 3 major income sources. With increasing drought severity, we do not really see that households are moving out of agriculture more, shifting, for example, into other activities. We also do not see effects for livestock, but they are less reliant on income from own businesses by about 27 percentage points. And we also see a lower reliance on remittances by about 19 percentage points with the 1 standard deviation increase in drought severity. This could potentially hint at a broader strain on the local rural economy because maybe food-related businesses are also affected, and also informal insurance networks might also be negatively affected if everybody is hit by a drought, for example. But we cannot really test these mechanisms. So then our last set of results looks at whether now farmers are sort of pushed more into adaptation, whether experiencing a more severe drought correlates with making plans for adaptation in the future. And so we asked them, what will you or other household members do to reduce the effects of a drought in the next 12 months? So as a sort of short-term horizon. And now think about the long term. What plans over the next 10 to 15 years are you considering or implementing to adapt to the impacts of frequent extreme weather conditions such as droughts and floods? So we broke it down into 4 areas, and this now regresses sort of adaptation, each of those 4 areas on our drought severity measure. We only really see a positive significant relation with planning adaptation through agriculture in the short term. So this is sort of the top row. We also see that there's a negative association between planning migration in the long term and having experienced a more severe drought. This could potentially be lack of financial means after the drought, so that they're relatively pessimistic about their potential to migrate. And so now this year we were interested to see, okay, did this actually translate into implementing any strategies? So again, we asked them now which strategies they implemented, and we do not see any association between experiencing a more severe drought in 2024 and actually implementing any of those strategies this year. And of course, you might now say, okay, implementing a strategy is a bit more difficult than forming any plan. So also we asked them again about their plans now for the future, for 2026 and the next 10 to 15 years going forward. And the same picture emerges. Even for future plans, we do not see any association between experiencing a more severe drought in 2024 and planning adaptation through any of those areas such as agricultural technologies anymore. For some reason, migration does not seem to be a very popular adaptation strategy, because here for short-term adaptation, we also see a very small but significant association again. So to wrap up, what have I shown you? So overall, we've seen that more severely affected areas face stronger yield losses in soybean, and there are implications for labor hiring and labor demand due to the lower hiring of agricultural labor. We're not able to look at general equilibrium effects here, of course, but this sort of provides at least suggestive evidence that there is something going on here. We see a lower reliance on business income and remittances in those more severely affected areas, potentially hinting at a broader strain on rural economies and a limited scope to switch or diversify income sources for farmers. So it seems that they're somewhat stuck in agriculture. Experiencing a more severe drought also encourages making adaptation plans for the future directly after the drought, but then 1 year later, this effect seems to have vanished, both for having actually implemented the strategy and for forming future plans again. And this is all, or findings are all in line sort of with the literature that's hinting at climate-induced poverty traps and farmers not being really able to truly adapt through more structural and transformational approaches. So there's a need for policies that enhance farmers' awareness and capacity to adapt to weather shocks, but also to generally improve self-employment and employment opportunities outside of agriculture for these farmers. Okay, thank you very much.
The difference in difference design is well motivated, and the balance test is reassuring. However, with only 17 community clusters, the identifying variation is limited. I would encourage the author to show event study pre-trained using the satellite rainfall data they already have. This would make the parallel trend assumption much more credible. I would also encourage a brief discussion of potential within community spillover, frog, labor, and input market, which could affect your individual level estimator. My second comment, This is the most striking form of a mobile phone heterogeneity within your paper. Phone user attend more cultivation, incur higher cost, and end up with significant, however, lower net income, but the mechanism remain unclear. This farmer action on poorly calibrated information, told to plant, they plant and they lose, or are they simply more motivated and risk-tolerant farmer regarding of the phone access? These two interpretations have very different policy implications. The first call for improving the quality and timing of information. The second suggests information alone is not the binding constraints. The paper needs to take a clearer stance on this. And my question at the baseline, none of your farmers claimed to already know everything they needed. Information gaps are real and well documented in your data. But do you know what specific information phone users actually received during the trug season? Weather alert, planting advice, market price. Without knowing the content of the information, it's very difficult to know whether the problem lies in the information itself or in the absence of complementary support. And without that, it is hard to turn your findings into concrete policy recommendation. Thank you.
Okay, thank you so much for all these comments, all super good comments, and we'll try to take them on board. And I unfortunately don't have now the information demand disaggregated by phone users and non-phone users. But we'll make sure to put that into the paper. I think I'll also use my time now to take in more questions, and maybe after the session we can also discuss more.
Thank you. Thank you very much. I think it's a very nice paper. Thank you. And so just one point I want to make is how this evidence, how do you situate it in the context of Ghana in terms of what exists in the literature? So let me rephrase. So, like when you show the motivation, right? So maybe I missed it. So do we have this? Have someone done something related to this? So how does this situate in what we know before in the context of the study? So I guess the point I'm trying to make is it's a very interesting study, but I just wanted to see how it contributes to what we know before.
Yeah.
In the context of the study.
Yeah. So we're definitely not the first people to look at drought severity. There are studies from Mauritania, for example, also. What our study does differently, or I think what really is a contribution of our paper, is the data that we have, because we really have data just before and after the drought. So we do not need to look with like a 2 or 3 year time gap on secondary data here, for example. And we have really in-depth insights into how farmers think about their adaptation for the future and their actual implemented strategies. So this, I believe, is where our contribution lies here. Of course, sort of the hypothesis that weather shocks negatively affect agricultural productivity is not very new, and so on. So I would say our paper is in line with what the literature finds and adds more depth sort of to how farmers are really thinking about adaptation, and also showing here in a context and with a crop that is already more suitable to droughts and more resistant, that even still those crops are affected, and yeah, that we might need broader policies. Also that farmers are really thinking about adaptation through agriculture mostly, rather than, as I said, more these structural approaches. So yes. Thank you so much for your question.
Thanks. And sorry for making you to repeat that. Maybe it's already in the paper. Maybe it didn't just come out very clear to me during your presentation. But the follow-up point I wanted to make is, I think the discussant mentioned on the parallel trend assumption.
Yes.
Do you have something on this, maybe in the paper, or is this something you check that?
We only have one pre-treatment period, so we cannot do a parallel trends check.
Those look like a family of hypotheses to me. Do you correct for multiple?
And no, we don't so far. Actually, that's on my to-do list.